Hi there, Kyle Sword with NSG Pilkington, and today I'm going to be doing an AIA HSW course with you about addressing the embodied carbon that's in Windows. This subject is near and dear to my heart. Lots of people are starting to ask questions, what you can do, and we're going to try and talk through the strategies and some of the science behind this. We are a registered provider of AIA courses. This material is subject to copyright notices, but if you're interested, just please shoot me an email and I can send you a PDF copy of the presentation. I won't go into great detail here, but essentially from the description, we're going to just be talking about the carbon impacts of Windows and how to try and make better choices around the materials that you select and the impacts that those products have. The key points here, we're going to be trying to talk about the differences between embodied and operational carbon. We're not experts, but we're going to try and give you a very high level understanding of this and how it impacts Windows. We'll talk a little bit about carbon usage and how that impacts climate change. And then primarily we're going to talk to you about the glazing and how way that those emerging technologies and some of the designs and material use and reuse have on all the implications around carbon with Windows. So to do this justice, we're essentially going to have to try and cover 4 different topics. We'll talk very briefly about glass history and performance. So I'll give you a feel for how buildings are maybe built and designed today, some emerging technology in this field. We'll talk through the basics around carbon of these materials, and then try and do some case studies as well and summarize this for you. So the reason we want to talk about this is glass in Windows has got extremely complicated in the last 50 or 60 years. I mean, essentially from the beginning of time until the 1970s, if you wanted to make a window, you made a big sheet of glass, you cut it into a rectangle, and you stuck it into a frame. It really wasn't much more complicated than that. This shows on the left, even in the 1980s, our sampling box was 13 pieces of glass, and we made a couple different colors, a couple different thicknesses, and everything that we made, all the performance data could be on one sheet of paper. Essentially, you look at this, what they started to do in the 70s and 80s, when window performance needed to improve, we would start going to slightly darker glass and then even added some reflective coatings. So it's like taking your sunglasses and going to a darker lens and even like a reflective lens. Glass really wasn't much more complicated than that. But starting in the 80s when the US oil embargo hit, now you start to have double glazed units and low E's and high performance products, and even dynamic products like these glasses on the bottom that change state depending on the need that you have. For just a single double glazed unit with a low E on surface 2, on the right hand side, this is one of our downstream customers today, they have 2 sheets of performance products just on that one material alone. And then you think of all the other complexity that comes in when it comes to bird safe products and fire rated products and blast resistant and all these things. Glass and windows are extremely complicated. And so trying to get this right in terms of existing buildings and new construction is just really complicated. So we're trying to try and demystify some of the issues around glass. So I've got this video to give you a little bit of a feel for how glass used to be made back at the turn of the century. So polished plate glass was one of the 3 key elements that was needed to create skyscrapers. You needed air conditioning, you needed elevators, and you needed polished plate glass in order to make something that was strong enough to withstand wind loads and pressure at high elevations. So this is how our company was started in Toledo, Ohio in 1898. This product started getting made in Europe in the 1830s, started importing to the US, 1870s started to get produced here. But really, this is a key element of how glass used to be made. So the impact that that's had is from the 1900s until the 1970s. Really, there were only 2 or 3 major manufacturers of flat glass in the U.S. We were one of those, and so as a result, our glass went into about 1 in 3 buildings that was built from the 1900s to the 1970s. The vast majority of those are monolithic glass. If you look at the overall built stock in the United States, it's about 327 billion square foot of area. 40% of that is monolithic glaze still, and 70% of that ish is still under code compliance. And so the vast majority of the built stock in the United States is poor performing. And if you look at New York City local on 97 compliance type issues, 90% of the buildings in New York City are still going to be here in 2050. So that means the majority of those buildings are poor performing, underperforming, and we've got to figure out a way how to retrofit and upgrade those buildings to kind of existing energy type performance. So contrast that to today, how most buildings get built today is with double glazing. I think 98% of the US market is double glazing, and most of that is a double glazed with a low E on the outside pane of glass. So surface two, the inside surface of the outer pane has a low E coating on it. It typically is like a ½ inch gap of air or argon. The larger the molecule, the less stuff there is there to do heat transfer. And then there's an inside light. But that's taken probably 40 years to fully adopt. It took almost 40 years to go from single glaze to double glaze, but this is really how most buildings get built today. In all cases, essentially what we're trying to do with windows and glass is we're trying to make those windows into a filter and an insulator. So if you think about a filter, this shows on the bottom right here, the sun's energy comes in as visible daylight, UV, and near infrared. And essentially what we're trying to do is filter out the UV, let in all the visible daylight, and keep it flat across there so there's no color, and then filter out the near IR. That's called spectrally selective. But if you look, 43% of the sun's energy comes in as visible daylight. So a super, super high daylight product, you're going to have about a 0.4 SHGC. So if you want lower than that, you're going to have to bring that down a little bit in order to reduce it. But essentially, we're trying to make the windows into a filter and an insulator. And by insulator, what that's doing is the sun's energy and room heat get transferred in waves, and they either transmit through something, they absorb into it, or they reflect off. And that absorbed energy reflects off or reflects back into the building. Essentially, that's what we're trying to do, is we're trying to manage those two things so that windows can be high performing as filters and as an insulator. So there's lots of things that we talk to people about when they're designing windows and buildings, but the three primary performance factors are U factor, SHGC, and visible daylight. So SHGC and visible daylight are pretty similar. SHGC is of the sun's energy between a ratio of 0 to 1, how much of that gets transmitted through. Same thing with the visible light, how much of the daylight gets transmitted through. So a 1 would mean 100% of it gets through, and a 0 means it blocks all the sun's energy. In addition, you're talking about U factor. U factor, the inverse, that's R value. So the lower the U factor, the better the insulator that is. And so like when it comes to wall insulation and things like that, people tend to talk about R value. A higher R value is a better insulator. So it's those three characteristics. And the key thing that I try and tell people on here is, those targets are important. But if you took, say, a 70% daylight, a 0.3 SHGC, and a 0.3 U factor, I could probably give you a dozen products that'll meet those three codes, but they might look dramatically different. So the key thing I tell you is make sure you're doing mock-ups, make sure you're actually looking at the product, and performance and aesthetics aren't mutually exclusive. You just need to try and understand both what you want it to perform like and what you want it to look like. So I mentioned that we're trying to make the windows into good insulators. And in terms of reducing heat transfer, there's loads of things that you can do in overall window design. There's setbacks, there's shading, there's trees, there's blinds, there's frit patterns and inner layers. It's all sorts of stuff that you can do. But in terms of center of glass, we're actually pretty limited in the types of things that we can do to make windows a better insulator. To reduce heat transfer, the things that you can do is you can go to a darker, more absorbing glass that reduces your heat transfer. That gas that's in there, you can use a better gas. So when you go from argon, so from air to argon to krypton, those bigger molecules do less heat transfer. And if there's a vacuum, you have no heat transfer mechanisms. And that's about 70% of the mechanisms of convection conduction. That percentage is about 70% of the overall heat transfer. You can use a better low E, so you go from a hard coat to say a single silver, double silver, triple silver, or you use more than one coating. So you can do a coating on surface 2 and on surface 4, or you can use more pieces of glass. So when you go from single glaze to double glaze to triple glaze, all of those things reduce heat transfer. But in general, really, there's two treatments that people do when it comes to dealing with existing windows and making them better insulators. One is they typically put in some sort of secondary glazing, so you add interior or exterior storm windows. Maybe you use low E's, maybe you use different things around that, or you do replacement windows. I mean, that's typically the two treatments that we see people do, but really that's the above list, that's the science of the things that we can do to reduce heat transfer in terms of center of glass. So hopefully that gives you a feel of how buildings have historically been built, what current code is today, what type of construction that we have. And now I want to try and introduce you to some new technology, some emerging things that might be interesting in how we deal with carbon and performance around existing and new buildings. So first thing I want to talk about is vacuum insulated glazing, or VIG. Not a new concept. The first patents on this date back to 1913, and the first commercial product has been around since 1997. But again, with a vacuum, there's no gas in there to do convection or conduction, so it's a pretty interesting material. But again, it's been around for a while. So, but it's why is it considered an emerging technology? And I'll go through some of the science of this material as well. So VIG is typically the same two pieces of glass that get used in an IGU, but instead it's very, very thin and very highly insulating. So the key benefits on that is because there's no gas, you get rid of the convection conduction component for heat transfer. It's thin, so it fits existing sash. It's lightweight, so in operable windows, you take out a 1/4 inch glass, you put in a 1/4 inch VIG, you don't have to change the weights. It avoids some known issues with the organic seal material, and I'll talk about that on the next slide. It's got good sound reduction values because it's got a vacuum, which also doesn't transmit noise, and it's fully reversible, and if you're doing it in existing windows. So comparing VIG versus a regular IGU, if you take that traditional IGU with those two pieces of glass, the low ion surface 2, and you just pull a vacuum on that center cavity, what's going to happen is the glass is going to suck together and the edge seals are going to suck in. Those edge seals, typically they're like a rigid spacer material like aluminum or steel, and then there's some sort of organic sealant like a polyisobutylene, a PIB, or some sort of glue that essentially seals that spacer to the edge. So the three tricks really to make a VIG compared to an IGU, the first thing is you have to have a pillar array in there. So these are little tiny metal or glass or plastic dots, something like that, that literally every inch you're going to have one of these little tiny pillars on there. So what that means is when that vacuum pressure, which is about 1 ton per square foot, sucks those two panes together, that little spacer array keeps the panes from collapsing. That pillar array then becomes your mechanism for convection and conduction through there. So on an annealed VIG unit, those pillars have to be pretty close so the glass doesn't touch. But on a tempered VIG unit, you can actually space those pillars a little bit further apart because tempered glass is a little bit stronger. The key on that then is once you get those spaced out, that spacing means that you can drive your U factor much, much lower on a tempered glass. But in either case, the same three mechanisms will apply. So you have to have a little pillar array to keep the panes from touching. You have to have a rigid seal on the edge so that edge seal doesn't suck in. Most times that's done with either a low temperature molten fritz. So think of a low temperature glass. The glass welds the edges shut, or you can have a glass to metal weld. So think of a glass metal weld like an old incandescent light bulb that went right into a metal screw. That was done with one of these glass metal welds. So they've been around for over 100 years, but you have to have a rigid seal on the edge. And the third thing you've got to do is be able to get the air out. So the way that you evacuate air out is you typically drill a hole, you vacuum the air out through that little hole, and then you seal that hole up with a glass tube. There's a couple new ways that are starting to emerge with this sort of technology, but it's really those three key mechanisms and how you make both annealed and tempered VIG. So just to give you a visual on what that looks like, on the left, you're going to see a typical commercial IGU, two pieces of glass with a 1/2 inch airspace in between. On the right is a VIG, so it's two thin pieces of glass with a really, really thin vacuum cavity in between the two. So significantly thinner unit once completed. So before people actually want to potentially use this product, a lot of questions I get is, well, what does it actually look like? Do you see those little pillars? Do you see the cap? Do you see all that sort of stuff? And the picture on the left here shows really highlighted these little tiny pillars. These are 0.2 millimeters round. So that's 1/128th of an inch. If you're sitting in a conference room looking at the glass and you put it on a white background, you can definitely see the pillars. In reality, once you have it installed in a window, it's pretty much invisible. Even if your eye knows that they're there and your arm's length away, they're really, really hard to see. In certain light conditions, you can see them, but generally speaking, they're invisible. The cap is definitely something that is going to be evident, and the picture on the right shows what this might look like as an install. It's fairly small. It's always going to be away, 2 inches by 2 inches away from one of the corners. And to be quite honest, and people get really nervous about this, what it's going to look like. From the exterior, you don't really see it at all. And from the interior, your eye actually looks right through the cap. So my personal feeling is in most projects, it's probably going to be okay. But it also depends on the taste and the aesthetics and people's willingness to accept that. So these pictures are taken from a big VIG project that we did on the MIT campus. And really, I mean, this is the key that you end up having with owners and designers is from the exterior, really those caps and pillars are pretty much invisible. It's all dominated by exterior reflection. You're not really going to see those things. In transmission, depending on the lighting conditions, if you're looking at a blue sky or a white background or something like that, you can see those caps. But again, your eye typically looks through the color black, just like you look through the muntins and mullions that are here. A lot of times the transmission, yes, you can see them in the right conditions, but honestly, your eye ends up looking through them in the vast majority of the time. And this is just another closer, slightly different angle that you're looking at them. But again, you can see from the exterior, they're pretty much invisible. And even from the interior and transmission, it depends on your viewing angle and what's behind it. But really, it's up to personal taste and aesthetic. But I mean, really, this is the payoff. And what we're talking about is if you're in New York City or Boston or Chicago or a lot of these buildings that are, humidity controlled, they got people living in them. On a cold winter day, it's 0 degrees outside. Your monolithic glass is about a 35-degree interior temperature, and a lot of times it frosts up on the inside. You can't see out the windows. And if you look at a VIG product, your interior temperature jumps up to about 58 degrees. This is one of the lower performing VIG products. It can bump up to about 65 degrees if you get the right type of product here. Stops your frosting, increases your comfort level. Really, from a retrofit, this is a really nice, easy, simple setup to do. So when I think about annealed vacuum insulated glazing, I think through, okay, well, what are the pros and cons of that sort of technology? So annealed VIG, again, this can be like 1/4 inch overall thickness, so it's a really thin form factor. It's still highly insulating. You can get anywhere from an R4 to about an R8 type performance with this. Simple change out for monolithic glazing. It's lightweight, so it fits in the same spot. And then it's got a superior seal durability because that it gets rid of the organic material that's on the edge. No more polyisobutylene or any of these seal materials. You have an inorganic glass or metal weld. What that means is that doesn't break down with time, temperature, humidity, moisture, and all these sort of things. So instead of a typical 10 or 20-year warranty that you're going to get, and that material eventually we know is going to break down, these inorganic seals have the potential to last 50, 60, 100 years. Nobody really knows the longevity yet, but the science behind that edge seal is it's got the potential to be a much, much longer lasting, more durable product. The cons on that, when you think about an annealed VIG product, it isn't safety rated. So there's some ways that you can get around that with doing some lamination or safety films, but it's not a fully safety rated product. Because it's annealed, you're going to have some potential for higher thermal stress risk. So you definitely need to do an evaluation on all the different projects. The VIG cost compared to an IGU, the VIG is going to be much more expensive. In ballpark terms, it's probably twice the cost. But the reality is you need to compare apples to apples on the overall project, because even though the glazing component might be more expensive, by reusing the frames, by avoiding landfill, by doing all that sort of stuff, your net project costs on an annealed VIG restoration are generally pretty good. And then the cons are there's definitely some aesthetic trade-offs in terms of the little cap that's in the corner. Compared to a regular monolithic piece of glass, you get a little bit more reflectivity. There's a low E on there, so there's maybe a little bit of color that comes into it. But that comes when you get any sort of high performance product. You're going to have to look at the trade-offs between the aesthetics and performance and make sure it's something that is a fit for the building. Now, in terms of those tempered VIG products, these are fairly new to the marketplace, but they're still around, and the technology has been around for quite a while. Because you have that wider pillar array that really drives down your U value, so you can get like an R10, even up to an R14 type product, really highly insulated and still a fairly thin overall profile. Because you've got a tempered product, you can then start to introduce some higher performance low E's. You can start to introduce some tints. You can start to introduce some different technologies. So it's a really interesting technology. Again, it's still fairly new in this space, but I think it's got a lot of potential. The three tricks on that in terms of making a tempered VIG compared to a annealed VIG. One, you have to have super flat tempered glass. Otherwise, what will happen is any sort of roller wave or distortion, the panes of glass will touch in between those little pillars. It'll short circuit and cause a premature failure. So you got to have super flat glass. That edge seal, that rigid edge seal mechanism, has to avoid detempering the glass. So you have to either have a really low temperature ceramic or that glass metal weld. Those all tend to be solvable problems, though. The tempered VIGs that are on the market have solved those sort of issues. The real challenge is still around tempered VIG, and even annealed VIG for that matter, is there's still not a lot of standards out. There's not ISO and ASTM standards that are fully agreed upon in order to what you test, how you test. Two fully tempered pieces of glass, if you break those independently, they'll break into really small pieces and they'll pass a tempering test. Once you put that into a tempered VIG and you break the tempered VIG, those little pillars cause weird stress islands. And so your break pattern might not break in small enough patterns to still pass some of those safety ratings. What's that mean? I don't know. That's just the reality. We're still working through all that sort of stuff. Failure mechanism on this, an annealed VIG when it breaks might break in fairly large chunks, but a tempered VIG is going to break like tempered glass. So the potential on this is it might break into really small pieces, and that break might transmit through from outside to inside since you got a rigid edge. So does that mean when it breaks, it fails and you got a big hole in the wall? There's a lot of things that we still have to work through in that sort of place. And then the other challenge is a tempered VIG is going to be more expensive to manufacture because you have to temper the glass. That's an expensive and high industrial process. And then those edge seal mechanisms sometimes are a little bit more difficult as well. So that's going to drive up the cost of the glazing material. So a tempered VIG is going to be more expensive than an annealed VIG. It's going to perform better, but what's the premium versus what do you actually need it to perform as? And so again, not saying you need this one's better all the time, this one's better all the time. There's probably a place for both of these in the marketplace, but you just have to understand the benefits and the cons for each of those products. So I've given you a good history on vacuum insulated glazing just because I think there's a really interesting place that this has in the market, both for restoration and for new building construction. But there are quite a few other alternatives that are starting to emerge, and I'm going to talk about those. I'm not going to get into stuff that's not commercially viable or commercially available at some point. There's things like aerogels and highly insulating materials that have promise, but really nobody's commercially selling those yet. So I'm not going to talk about things like aerogels and other technologies. I'm also not going to talk at great length about some other products that are on the market in the dynamic space, like switchable materials and electrochromic materials and stuff like that. I mean, those are commercially available. Those have very interesting place as well. I'm just not going to talk about those in terms of this subject material, just because in terms of carbon impacts, I don't have a great background and history on those sort of things. So I'm going to talk to you about technologies that I know that are emerging in this space, and they're essentially really talking about energy efficiency, and then I'm going to be able to explain the carbon impacts around those sort of ideas. So I've already talked about VIG at great length about how simple reglaze with VIG might make sense if you've got an existing building that's monolithic glazed. Some of the other places that are pretty interesting is, secondary glazing has been around forever. Interior, exterior storms, most times that's, single piece of glass, maybe a single piece of glass with a low E. But now what we're seeing people do is using thinner glass. So this might be like a 1 millimeter thin glass, or it might be a few pieces of thin glass that then allow you to have a lightweight solution that instead of bumping you from an R1 to an R3, this might bump you from an R1 up to an R7 or something like that. So really, really high performance. You can use that VIG as a secondary glazing in a lot of applications. And there's also what's called overcladding, where you're actually taking and making an IGU in situ on top of an existing building. So the seal mechanism is much more profound than just a regular secondary glazing. It's not going to have this the sort of maintenance routines that normal storm windows are. You have to go in and clean. This is avoiding a lot of that. Really some interesting stuff that's going on here in terms of how to deal with an existing monolithic glazed building. And it focuses a lot around energy performance, around weight, and around seal technologies. And so there's a few different things here that are pretty interesting. We're also seeing some new technology that's addressing how to combat the existing 98% of the market that's just double glazed. Again, triple glaze has been around for 20 or 30 years, but it's only 2 or 3% of the market. And traditionally, that's because when you go to triple glaze, you have to go from the traditional crank windows that we have in the US to tilt and turns or to fixed windows. They're super thick, super heavy, super bulky, and they're quite a bit more expensive typically. So what we're starting to see people do is say, how do we get the performance there without having to change that form factor? So the thin triple IGU is an interesting concept. What this does is it takes a traditional double glazed IGU and it sticks a piece of 1 mil or some really thin glass in between. Now you have a significantly higher glazing component, but you don't have to change out your overall form factor. So in a new window, you can keep the same extrusions and drop this in the same spot. in an existing, say, 1970s curtain wall that's failing, you could take out that double glazed unit and you can stick in a triple glazed unit in the same spot. So it gives you some of the same opportunities that you can do with VIG, slightly different technology. You can also use what's called a VIG IGU hybrid. So instead of the regular double glazed unit, your inboard light, typically you could then make a VIG unit. So now essentially you're getting a triple glazed performance or better because you're including that VIG tech into a regular double glazed unit. And then again, dealing with weight scenarios, we're starting to see people start use thin and thin laminates as ways to address this. That way you're not taking all that extra weight into the window and framing units, and it's also avoiding having to put all that different shear weight on the skin of the building. And there's some other benefits that goes along with that as well. So some interesting technologies that we're starting to see grow. So again, just very high level with some new technologies that are coming into this window space, how they might potentially play out, how they're built, how they perform. So now what we're going to do is try and look in depth at the carbon issues that go around these different technologies and how some of these emerging techs really start to change your carbon form factor and your performance in terms of buildings. So in terms of carbon, most people are really familiar with what's called operational carbon. So how much energy, what's the energy efficiency of this building? What's your HVAC? How much heat do you take to heat it and cool it and lighting and all those sort of things? You've probably heard many times over that buildings consume 40% of the energy in the US. Most of that time, people are talking about operational carbon, but really we need to talk about operational carbon and embodied carbon. Embodied carbon is how much energy does it take to melt the glass and then make the window units? How much energy does it take to make the steel and carbon and all the building materials? And also you then need to consider how much energy it takes to operate the buildings. So the historical focus has been on operational carbon, but really we need to focus on both operational carbon and embodied carbon and make sure that we're trying to do the right thing on both of these materials in order to reduce the overall energy consumption of buildings. So in order to understand this, what we first did was said, well, where do we really fit in the big picture? How much is glass a player in terms of the operational and the embodied carbon? So this first study is a study that was done by Getzler. So what this says is if you look at an overall building design, where does all the embodied carbon come from in terms of the materials that you use? And what you find is, glass is a very, very small portion of that. Typically, we're between 2 to 5% of the overall embodied carbon of a building. The vast majority, 70% or so, is the structural element. So if you think of like glass is energy intensive to make, but realistically, it's a very small portion, and that makes sense because the glass is just the skin of the building, kind of like the rind of the watermelon. And even though carbon of concrete, itself may not be much per pound, you use an awful lot of concrete into building construction. So really, glass is a very small portion of the overall embodied carbon up front. And if you look at that building sector, buildings consume 40%, 2/3 of that's an operational carbon, and then 1/3 of that is embodied carbon. So the first thing we did was we said, well, how much does the glass impact that overall embodied carbon? We're a small portion of it. And again, doing some really quick math and the logistics of this, we went through and said, okay, the overall glass industry, not just flat glass, but flat glass and bottling and glassware for plates and all sorts of stuff. All of those industries combined only use about 0.2% of the overall energy used in the United States. So in terms of manufacturing, there's a lot that we're doing to reduce carbon, and I'll talk about that this year shortly, but really big picture, we're a really, really small portion of the embodied carbon of the US consumption. But in terms of operational carbon, windows have a significant impact in that. So if you think about building operations and all that goes into heating, cooling, lighting, and all that sort of stuff, if we just took that existing built stock and brought all those older buildings up to code, that can actually have a really, really much more significant improvement in reducing the operating carbon. So what we're trying to figure out is how do we position this in a way that makes sense for people to say, yes, we have to reduce the operating carbon that is made in glass, but really it's a factor of 10 or 20x is the impact that the glass and windows have on operational carbon. So if we really want to reduce carbon, we need to try and make sure that we're putting in higher performance products in order to best suit that demand and need. So I mentioned that glass is energy intensive to make, and we're actively working on a number of different things to reduce the carbon that goes into glass. We've done a number of different trials at our plants in the UK where we did hydrogen firing and biofuel firing. We're actively putting in a lot of solar arrays at our plants and different trials that we're doing there. We're trying to electrify our grid, be able to be more energy efficient, a wide variety of things. And we've got some significant target reductions by 2030 and carbon neutrality plans that'll get us there by 2050 based on science-based targets. So we're actively doing a number of different things in this space, trying to reduce our carbon impact with our manufacturing. And we're working with customers as well to say, how do we help you reduce the impact of the glazing and glass that you have in your building design? And so one example of this was we did a project up in Detroit. This is the Albert Kahn building. This was an 11-story building built in 1931, bronze double-hung windows that were single glazed with quarter-inch clear glass. And so they were going to go and upgrade this building. And we said, well, you could do replacement windows, you could do interior storms, you could do exterior storms, you could do steel or aluminum framing on that, you could do a VIG reglaze. So we tried to look at and say, what are all the different alternatives that you can use? And how does the carbon impacts of the embodied materials and the operational materials weigh out? And the thing that we found on that is kind of intuitive and makes sense. The less stuff that you add, the less of embodied carbon you add. And so a reglaze of the existing materials adds the least amount of embodied carbon, which should intuitively make sense. But then if you couple that with the operational carbon, the thing that we found, and again, I was a little surprised at this, is the operational carbon is significantly more than the embodied carbon. Operationally, this building consumes about the equivalent of 1,200 metric tons of CO2 per year. And even the highest embodied carbon material of an aluminum window replacement would have only been about 100 tons. So it was significantly less than the operational carbon. And then if you look at how much impact we have in savings, with any of these alternatives, we're able to save the operational carbon from 160 to about 230 tons of operational carbon per year with energy efficiency improvements. So we then started saying, well, what does that mean in terms of payback? How quickly do we pay back the embodied carbon debt of the window and glazing materials with improvements in operational carbon? And with any of these, it was really short. It was between 1 to 5 months. So the key thing on this is they ended up doing a VIG reglaze. It was about a 13% energy savings on making that building more energy efficient through the reglazing. And that payback was in about 1 month. It was actually reduced the net carbon of the overall project. So significant in terms of how much of an impact we can have in terms of operational, and really in comparison, a minor impact in terms of the overall embodied carbon additions that get into this project. So when it comes to working with projects and designers and people that are dealing with carbon and energy efficiency in buildings, there's really a 3-tiered approach that we're starting to use. So the first thing we're doing is saying, okay, well, in terms of carbon reduction, what can we do to help designers and building owners reuse their existing materials? So this can be in reglazing the existing framing, this can be in adding secondary windows, this can be in lighter weight options. There's a number of things that we can actually do to help people reuse their materials. We've done a number of these with, Empire State Building. Originally, they did a reglaze of that using a film in the center as a retrofit on site. That was done several years ago. And now they're even looking at higher performance interior secondary glazing type options. So things that we can do to help reduce the amount of materials and reuse the existing materials is really one of the strategies that we'll have. One of the other ways that we help people is help reduce the impact of the glazing material choices that we have. So if you look at that thin triple IGU, the embodied carbon that comes with each piece of glass is fairly linear to the amount of weight and thickness that you have. So by using a thin triple, you're actually adding a lot less embodied carbon just through the different types of materials that you can use. So if you can use things to lightweight this, you can use things that drive forward your operational carbon performance. There's a lot of things that we can do to help you reduce the overall footprint of this. And one of the key things that we're doing is working with groups like PAWS, the Partnership for Advanced Window Solutions, and trying to figure out how do we advance the adoption of new technologies in this space to help speed up the performance of these type of buildings. So we're doing a number of different things to help people reduce the carbon impacts of their design. And we're working on a number of ways to help revitalize the types of technology and glazing that get put in. So this is in things like using transparent photovoltaics in the visible areas, building integrated photovoltaics where your window becomes a solar generator, These could be in things like dynamic glazing and electrochromics and other materials, but there are a number of new technologies that can also be implemented that help this overall performance, carbon, and energy efficiency metric on-site power generation. So we're trying to work with a number of different technologies in this space as well. So now I'll talk through some different case studies, some things that we've done, and maybe a few more examples around carbon and impacts, and just overall in the window design, what sort of performance are we getting and how do we help? So one of the first case studies I'm going to talk about is a landmark building designed by Eero Saarinen. This is the Milwaukee County War Memorial. So this is a steel frame construction. It was 1/4-inch wire glass with metal frames, hugely energy inefficient. And this was originally the architect was hired to do a curtain wall replacement on this. And they wanted to go and dig in and say, well, what other potential options do they have? So when we looked at the framing and glazing components, what we see is this is a fairly thick steel recess, and we could have taken off the glazing beads and actually installed a 1-inch IGU on this, and there was no reason it couldn't accommodate that, and energy performance would have been pretty good, and really wouldn't have changed the aesthetics on that building enough that maybe it was a big issue. The challenge with that is then you have to re-tap 13,000 glazing bars and re-drill those holes and fill the other holes and deal with the corrosion and all those sort of things. So the cost of that became a real issue. A monolithic reglaze, even with like a hard coat low E or something like that, didn't necessarily get into the performance benefits that they wanted to. And a full curtain wall reskin was going to be pretty expensive and really change the design that Saarinen had. So they ended up just doing a simple reglaze with VIG. They kept the same glazing bars, they kept the same holes. It was a much faster installation. It was a much lower cost installation. It still got them to the performance levels that they wanted. And in terms of the carbon impacts, least amount of embodied carbon, significant improvement in operational carbon, really wins on pretty much every bit of the scenario. And the net project, looks pretty much like the original. So from a historic aspect, it was great as well. So nice, simple win, simple solution sort of thing. And then this is another project we just finished up in New York City. This is the Tiffany building. This is stainless steel true divided light. They went into different options because they wanted to keep these original stainless steel windows. I mean, they're really, really well done, very nice. And changing that, I think, probably would have changed the aesthetics of the building pretty significantly. But they had options. They looked at tempered VIGs. They looked at a number of different ones. And they were trying to weigh out the difference in terms of aesthetics and cost and performance and how the overall building performed. So if you look on this, they have about an R1 frame. Stainless steel is a pretty high conductor, but an R1 center of glass because it's just 1/4-inch monolithic glass. The interior temp on that's probably about 38 degrees. You get some frosting, and really from a comfort level, an R1 you can't sit within about 6 feet of it comfortably. So it's really not a comfortable space for offices and such. So afterwards, you take an R4 center of glass, and we could have put in higher performance products, but it changed the footprint, it changed the installation designs, it changed the aesthetics of the buildings. That all went into consideration of what you chose. But if you take an R1 frame and an R4 center of glass, overall you're getting to about an R2.5. So maybe that's not quite as high performance as a full replacement window would be, but it's still a significant improvement while it keeps the existing framing and minimizes your additional carbon improvements, and it makes some operational improvements as well. Takes that interior temp up to 58 degrees. Now you can sit within 2 or 3 feet comfortably. But the framing's still the weakest element. It needs to definitely be a part of the consideration. And another thing we could have looked at is, an interior secondary glazing with a storm system using a VIG. That then takes your interior temp up to 65, 66 degrees, but you lose operability. There's other changes that go along with that. So it really depends on the project. And you're going to have carbon impacts, operational impacts, and embodied carbon impacts with all of those choices. So really, these are just things that you can use as tools, and you got to evaluate each project on a project by project basis. MIT is the largest VIG project in North America. This was started in, I think, 2014, and it was a 3-year study done by MIT. They took these different classroom bays, 20 foot tall by 8 foot wide windows, and they did one as a VIG reglaze. They did one as window replacement with a thermally broken sash, and they did one as secondary glazing. And they said, well, what are the different options that we have? They did thermal scans every quarter. They looked at operational performance. And after 3 years, they went with replacement non-thermally broken metal sash with VIG as the true divided light glazing, because they said that had the least impact on the aesthetics of the building. It kept truest to the original design, but it also got them the energy performance and the potential longevity that they were looking for. It was the only product that they felt could probably get them a 50-year life cycle, and the comfort and energy efficiency that they were targeting. So again, the study's not been published. It's all internal to MIT, but there's a few different stories on this that I could probably share with you. But it's a really interesting one, and some good research that went into it as well. Another project in New York. This is a professional children's school on West 60th. This is where a lot of Broadway kids that are on Broadway and acting, they go to school because they have non-traditional school hours. But this was done in order to get energy efficiency for the building. Again, it was casement steel windows, true divided light, non-thermally broken framing. They were doing it for energy efficiency, but the biggest improvement was actually in the acoustics of the building. They said they used to have to stop class when a truck would go down the road, and the acoustics of a VIG are similar, or maybe a little bit better compared to a similar IGU. So it's going to be a significant step up over monolithic glazing. It's another example of a project where it was true divided light, steel sash was reglazed with VIG. But just to give you an example of some of the large buildings you can do, this is a GSA-owned building, the Seattle Federal Office Building. Again, not the coldest climate, not the warmest climate, but a significant energy efficiency improvement with a fairly simple retrofit of just reglaze the existing windows. Here's a slightly different project. This was a project that was in Vancouver, Washington, monolithic glazed 4-story building that was really just unmanageable with the HVAC systems. As the heat waves and as climate change has kind of impacted these things, you're starting to get quite a few more 100 to 110 degree days even in Washington. And these buildings that just weren't designed for it. So you're getting offices that are 90, 95 degrees even with the HVAC system maxed out. So they're getting to where they're just unmanageable with the systems and really unlivable in terms of people couldn't occupy that space comfortably. So what they did was they came in with a secondary glazing system. It's a high performance, it's a double glazed lightweight interior fit. That solution ended up giving you about a 13% or greater energy savings. But more importantly, it actually made the building livable. It made the space you can manage and maintain the temperature even on the south face, even in the most direct sunlight, and much more comfortable for the occupants. So this was a U.S. Glass Best Green Project Award winner. So really, again, innovative solution, a new market type thing. So in terms of old building design, new construction design, I tried to give you a little bit of a flavor for the types of ways that we approach glass, and then with some of these emerging technologies, some new tools. So if I try to summarize that into what does that mean and how do you start to use these tools for best energy efficiency or minimizing your carbon impacts, I'm going to try and spell out some of those things in terms of how I would address existing buildings and then how I would potentially address new construction. So if you're dealing with an existing building and are just wondering, why should I try to do some of these restoration methods instead of just doing a full rip out or something like that, there's definitely some pros and cons with both approaches. But there's really a lot of nice benefits that you may want to consider. Again, every project's different, but just use these in the way that you evaluate the projects. But existing buildings, you can get a significant upgrade even with your original framing and the acoustics by using some of these technologies. You can get some pretty significant energy efficiency upgrades. You'll dramatically improve the comfort level of people that are sitting in there next to you. So yeah, you can get some of those things with HVAC systems. You can reduce your carbon impacts. You can reduce your make your building more energy efficient. But the comfort level of what it is when you're sitting next to that glazing also matters for your occupants as well. Properly restored buildings also tend to maintain and keep their property values and keep higher rents than do buildings that have been somewhat shoddily reskinned or retrofitted. So again, it depends on, are the original materials a good enough quality? Is the design important? Is it historically an issue? Really, a lot of it depends on what the building looks like and how it matters. The carbon payback in all these things is actually pretty significant. And whether it's retrofits, whether it's in full replacements or whether it's some sort of a secondary solution, they all have pretty good carbon impacts. But really, it's how do you make the biggest bang for your buck and over what time frame do you want to do that? All that matters. So you want to take that in consideration. Um, from a resiliency standpoint, we also like to think about buildings and that how do they deal with, with the changing climates, the impacts that this has, and what happens when the power goes off. If you have systems that are fully reliant on your HVAC systems, like in Texas last year, we had cold spells and the power went out for days, and we had, hundreds of people that died as a result of these cold spells. Having buildings that are more sustainable and more resilient to those sort of climate extremes is really, really helpful in a number of different ways. It also helps future-proof your gas prices. Right now, it's cheap just to add a little bit of heat in the winter, and it keeps your home livable. But really, if the price of gas is potentially volatile, as we're seeing in Europe right now, who knows what the future holds? These sort of systems, you have to start to consider that in the way that you look at the project. Generally, the systems that I talked about today are all manageable supply chain. So it's not like, there's one person in the world that's starting to create a lot of these. There's a number of players in this space. Timeframes, lead times, and costs should all make these manageable things that you can actually really evaluate and look at. And then potential longevity, if you have a window right now that lasts 10, 20, 40 years, that starts to really impact your both the cost effectiveness of that product, but also the carbon impacts of that product. And so really that's going to start to become a more significant issue. In terms of some of the higher performance secondary glazing systems, that starts to play into weight. It starts to play into form factor on the structural elements that you need to support those heavier things, but it also starts to play into the projects themselves. And if you have an existing building, whether it's a residential or commercial, can you go in there and add that secondary system overnight so it doesn't disrupt somebody, or can you do it over a course of a couple of days instead of a couple of months? That starts to have real value in terms of projects as well. And if it can get you the energy efficiency and comfort levels you want, that maybe is also a different one. So we're starting to see quite a few different benefits from these systems that really are starting to move the needle. In terms of cons, I would say the one thing you have to look at is what you're fixing up worth fixing. If you think about old growth wood or some of the historic steel that are made, there's bronze and stainless steel windows that nobody could really afford today. I mean, there's obviously some, but maintaining a lot of those historic things, really you have to start looking at, does that make sense? But it's really got to be something that's worth saving and can actually last if you are going to save it. In terms of some of the products that we mentioned, even though they're technically available in certain sizes, you may not realistically want those in all those sizes. There's more of a sweet spot, especially when it comes to safety applications. Floor to ceiling stuff tends to have to meet safety code. Some of the annealed VIGs aren't going to meet that. So really, like the annealed VIGs, even though you can make them in up to, say 80 square foot panes, really those more sweet spot on your projects is maybe more the operable windows, the stuff that's not at, above 18 inches and is maybe smaller than 25 square foot. You start to have to look at all that. In terms of your glazing contractor, a lot of the commercial glazing contractors that do the curtain wall systems or punch window installations, those may not be the same people that you end up using when you do a retrofit or you do a reglaze of existing building. A lot of times you got to have people that are knowledgeable about those historic materials. And you're also going to have the expectation of some more upfront costs when you're trying to get the right sizing and the right framing, and how do you clean it up, and if you have to do asbestos abatement. I mean, there's a load more stuff that goes into some of these retrofit systems. You also may be limited in the types of SHGC that you can achieve. So your really low SHGC products tend to have to all be tempered because you induce a lot more thermal stress with that. So you're limited in some of your SHGC goals. So maybe these aren't really great solutions in terms of, really warm climates or in certain types of retrofits, because you not only have to think about the thermal stress and the stress conditions and wind load on what you're adding, but to the original glazing materials as well. And so if you have a tint or you have something else that's there, you could potentially add a material that then introduces thermal stress on your existing window and causes breakage. You also have to think about things like, fit and air leakage and all those other sort of things. And then the last thing I would say is you also might need more than a simple retrofit to get you to your 2050 targets. And so I wouldn't want to recommend to somebody do this to get you compliant with your 2024 targets, and then in 3 years rip it out and put something else in. So really, all those things need to be considerations. These are just tools that you can potentially use. And then these emerging technologies and carbon considerations, the way I think about this in terms of new construction is, a hybrid VIG is available today. There are people that make it, and it's a pretty simple plug and play. You take out your 3/4 inch IGU, you stick in a 3/4 inch hybrid VIG. Yeah, your cost of your glazing goes up, but you have a system that you don't have to change out your weights and sizes and all the, the design. It's a plug and play that you can stick in, so it's a really simple fit. Um, a lot of these things are also slimline that actually meet some of the codes, some of the requirements, and some of the extrusions that you currently have. So they're a really nice fit. If you want that super high performance product, if you're looking for something that previously has only been able to be achieved with a quad or with a quint, and it's 4 inches thick, these tempered hybrid VIG IGUs can get you to this R12, R14 type performance in what's traditionally a regular glazing configuration. So those are nice fits if you're really targeting a super high performance product. You're going to end up paying more for it, but it's going to be a really nice high performance product that's not been available before. And then the last thing to me on this as a pro with these is, to me, when I look at a lot of the 2050 targets in different cities, I think you start running out of low hanging fruit. You start running out of the LEDs and the HVAC system upgrades. You're going to have to tap into the facade to figure out how do we future proof and get this building to be a super high performance product. You're going to have to start including some of these other new technology, I think, to be able to achieve some of those. So that to me is the pro on why you'd want to consider these. I mean, the cons is as you deal with these safety issues and the supply chains of some of these tempered issues, it starts to become a bigger issue, because now it's, do you have you need this testing protocol to do this, to get this as an NFRC certification. These are still emerging technologies, so some of this stuff is still in development. And if you have a 3/4 inch or 7/8 inch IGU that meets your needs today and is code compliant, and people are happy to buy it, and what's the motivation to go to a thinner product that does a little bit better than that? So you have to have some driving factor to say, this is what's pushing me into this technology, because just going to a thin, creating a window that's got a thinner extrusion to lightweight your window a little bit. I mean, the benefit is you take out all the metal from the framing, and you have to, then the wall thickness that can be accommodated in is significantly different. But beyond that, if it's giving you the same type of performance, there may not be a driver for it. And there's a lot of times not a big motivation to put in products that greatly exceed code, especially from a developer standpoint, is if you're going to develop this building and sell it and it meets this amount, if the cost of the HVAC systems is a little bit more expensive to the occupant, that's not really in the developer's interest to put in this super high performing product if they can't get it back in lease rates. And then lastly, in terms of some of these technologies, the VIG, it tends to be more expensive than traditional double glazed, single glazed insulating units. And so if you can achieve some of those performance products with a lower cost technology, eventually that lower cost technology ends up taking off. So right now there's a sweet spot, because you can hit some of these VIG products, can hit some of the performance levels that we're trying to target better than anything else. But eventually these other technologies will start to take over, figure out how to do it, and maybe figure out how to do it at a better cost. And so, eventually, that'll start to normalize out. So that is it for me. I try to finish on time, leave time for questions. Again, more than anything, what we're doing today is trying to just introduce this topic and say, here's different technologies that we're using today. Here's emerging technologies that can impact both operational performance and operational carbon and embodied carbon. Here's how you can use these things as tools in your toolbox, things you might want to consider, and just basically new ways to look at this. If you have questions, we're always happy to help. We'll look at a project and give you an honest answer and say, this is probably a fit for this one probably isn't a fit for that, and just really try and give you some guidance. So I hope it's been helpful and interesting. Thanks again for your time, and let us know any questions that you have.